Your modern stove is a luxury of convenience, but for the vast majority of human history, we were simply prey in the dark. We lacked the advantage of retractable claws or thick protective hide, and the night was a place where things with better eyesight and sharper teeth waited for us. There is a single chemical reaction that fundamentally altered the architecture of the human brain, and today we are going to find out how that happened. Now, fire is notoriously difficult to study in the archaeological record because it's ephemeral. Evidence like ashes can be swept away by a light breeze or washed away by a single rainstorm, leaving us with a narrow, flickering window into the moment we stopped running from the flame and started owning it. Consider the Pleistocene. It is a world of absolute crushing darkness, punctuated only by the same natural phenomenon that terrified early humans: lightning strikes. In the ancient forests, a single bolt into a dry tree could ignite a wildfire, sometimes triggered by the other common cause of natural flames: volcanic activity. For the first hominins, fire was not something they created, but something they kidnapped. They likely transitioned to scavenging burning twigs from these wildfires to start their own small fires, treating the flame as a precious, fleeting resource that could vanish at any moment. It is a terrifying thought, being the only animal in the forest that cannot see in the dark. Those few scavenged embers became the first borders, a small circle of light creating a fragile, flickering perimeter against the predators that waited just beyond the glow. The darkness was total, and for 1,000,000 years, the only thing keeping them alive was a few glowing pieces of wood. Enter Homo erectus. This species dates back approximately 1.89 million years and stands as the primary candidate for the first hominin to master fire. Why? Because they had a problem with energy. Homo erectus possessed traits requiring high caloric intake, specifically a larger body size, more muscle mass, and a larger brain. This is a biological tax. You cannot fuel a larger brain and a more muscular frame on raw tubers and tough grasses alone. Interestingly, Homo erectus had smaller teeth than their predecessors. This suggests they didn't need heavy-duty chewing for raw food, which is a strong hint that the food was already softened. This biological shift coincided with a massive geographical move. Homo erectus was the first hominin known to migrate out of Africa, spreading into the Republic of Georgia and Southeast Asia. They didn't just change their diet, they changed the map. Moving into these diverse, colder environments required a portable way to stay warm and safe, making the mastery of fire not just a convenience, but a requirement for survival. There is a profound difference between seeing a fire and owning one. For a long time, our ancestors were simply opportunists, kidnapping flames from lightning strikes and tending them like fragile pets. But the transition to truly controlling fire changed the map of the world. By harnessing fire for warmth, these early humans were able to expand their geographical range and migrate to different climates. Suddenly, colder and harsher environments were no longer death sentences. Regions that would have been frozen wastes became survivable, and as they moved, more foods became edible. It wasn't just about the heat. The fire provided a physical barrier against the things that hunted them in the dark. Imagine the patience required to keep a single ember alive for days while walking across a savanna. If that ember died, you didn't just lose a tool, you lost your only shield against the night. This was the first real leap in human technology, the ability to carry a piece of the sun with you wherever you went. In the early 1980s, archaeologists working at Kubifora, Kenya, noticed something strange. They found reddish-orange sediment patches, baked, rusty patches of earth that looked exactly like the ground had been burned. These red and orange sediments were found right next to a fossil hominin jawbone and stone tools dating back 1.6 million years. Later, excavation at Kubifora revealed shards of rock heated to extreme temperatures and clusters of burned animal bone. Because these were clustered in small patches, it suggests the fires were intentional, not just a random wildfire from Lake Turkana. These burned rocks and bones were associated with artifacts likely made by Homo erectus. But there is a puzzle. The only hominin fossils actually found at Kubifora were of Paranthropus boisei, a smaller brain species. Then we moved to Wonderwork Cave in South Africa, which is 1 million years old. Here we found burned bones, plants, and Acheulean tools, such as hand axes. Since these materials were found deep inside a cave, it means fire was being brought into human space. Finally, at Gesher Benot Yaakov in Israel, a site about 790,000 years old, researchers found burned seeds, wood, and flint in what they call phantom hearths. These clusters suggest our ancestors were no longer just scavengers of flame. They were creating fire at will. Now we have a problem. The biological evidence for cooking suggests a massive leap in energy, but the archaeological record is curiously silent. Look at the Dmanisi site in the Republic of Georgia, dating back 1.8 million years. There is no evidence for fire there, despite winter temperatures that were only slightly above freezing. This creates a gap. How did Homo erectus grow larger brains and bodies without the calorie boost of cooked food? Some researchers suggest that high-quality cutting tools may have allowed early hominins to break down meat before consumption, providing the necessary calories without fire. It is a mechanical solution to a biological problem. Others argue that hominins in Europe simply coped with the cold without fire, relying on cultural adaptations like basic clothing, shelter, or seasonal migration. It is a strange thought. Our ancestors were walking across freezing landscapes, potentially without a single spark, and yet their brains were expanding. The math doesn't seem to add up. Then we have Homo heidelbergensis. This large-brained species is a strong candidate for the firemaker at Gesher Benot Yaakov and throughout Europe, acting as a likely last common ancestor for both humans and Neanderthals. In the Levant region of the Eastern Mediterranean, evidence for regular cooking behavior becomes clear about 350,000 to 400,000 years ago. At the Daughters of Jacob Bridge in the Golan Heights, researchers found heated fish teeth deep in a cave, suggesting a deliberate diet of cooked food. This pattern continues at Kesem, where a large central hearth was used repeatedly for roasting meat, with charred remains of food plants and fish nearby. Around 400,000 years ago, fire use firmly establishes itself in colder European climates. We see this at Beech's Pit in England and at Schoningen in Germany, where heated flints and charred wood were found. But the real breakthrough came from researchers at the British and National History Museums in southeast England. Working at Barnham Forest near Thetford in East Anglia, Suffolk, they uncovered what they describe as the earliest evidence of deliberate firemaking. Published in Nature, the research shows that more than 400,000 years ago, early humans were not just tending fires, but creating them. Fool's gold, a mineral that's useless for jewelry but priceless for survival. These humans used iron pyrite, striking it against flint to produce sparks. Since they didn't have steel, the iron pyrite was their only way to summon heat. This discovery pushes the timeline of fire creation back by about 350,000 years compared to previous evidence. It turns out that 400,000 years ago, the spark was already in their hands. Cooking is not just about flavor. It is a biological shortcut. When early humans cooked food, the heat breaks down large, complex molecules into smaller, simpler nutrients. This makes the meal easier to chew and digest, essentially starting the digestion process before the food enters the body. It is a massive energy win. By breaking down toxins from roots and tubers and killing pathogens from meat, fire saves the body from investing energy in defense. This makes cooked foods more energetically efficient, providing more calories than a 100% raw diet allows. But there is another theory. Some scientists believe that fire was not primarily for cooking, but was a tactical tool for protection. This is the meat bank theory. According to this, early humans used fire to protect huge megafauna carcasses, such as an elephant, from scavengers. Instead of eating the meat same day, They used a perimeter of fire to keep predators away from the meat bank. The campfire didn't just provide heat, it provided the first real room in human history. Before fire, the day ended when the sun went down, but with a controlled flame, the night became a usable space. This created a new social architecture. Around a fire, early humans weren't just surviving, they were congregating. This is likely where the first complex social bonds were forged, and where language began to evolve from simple warnings into storytelling and planning. Fire effectively extended the human day, giving our ancestors hours of cognitive downtime to interact, share information, and develop the cultural cohesion necessary to survive in a hostile world. It was the first time we created an environment that didn't depend on the weather or the time of day. It is a strange irony that the most fundamental shift in our species' history is recorded in something as fragile as ash. A single rainstorm can erase 1,000 years of campfire evidence, leaving the archaeological record looking like a series of disconnected dots. Yet, while the ash is gone, the biological change is permanent. We don't have to look for burned rocks in Kenya to know that fire happened. We can just look at our own guts. Our shortened digestive tracts and our massive, energy-hungry brains are the living fossils of the first cooked meal. We are, quite literally, the children of the flame. We have the evidence of iron pyrite sparks from 400,000 years ago, but that doesn't mean it was the first time. It is far more likely that the first spark was struck hundreds of thousands of years earlier, and we simply haven't found the right piece of rock yet. Did Homo erectus have a method of fire starting that we can't detect? Or were they simply the most patient scavengers in history, tending a single flame for generations across a continent? The gap between the biological need for calories and the archaeological evidence of the spark remains one of the most frustrating puzzles in paleoanthropology. From the red-orange sediments of Cubiphora to the iron pyrite of Barnum Forest, the taming of fire was a slow, messy process. It took roughly 1.8 million years for us to move from kidnapping lightning to summoning sparks from stone. This transition allowed our ancestors to fuel a brain that consumes 20% of the body's total energy, a biological luxury we only afford because we stopped spending all our time chewing raw roots. The irony is complete. We started by huddling around a small, flickering ember to keep the leopards away, and now we use the same chemical reaction, controlled combustion, to launch rockets into the vacuum of space. We went from fearing the lightning to building the engines that can leave the planet behind. The question is, if we lost the spark today, how long would it take us to remember how to protect the perimeter?